Okay, welcome everyone. So today we're going to talk about union find. It's an important data structure in computer science, so let's dive right into it. So union find is also called the disjoint set data structure. You might have come across it either when studying the Kruskal's algorithm, the one of the minimum spanning tree algorithms, or in general as well. So the main purpose of the union find algorithm is it helps you maintain the sets dynamically. These are set membership structures where a set can be merged, which is called the union operation, or you just are given an element and you want to find out which set that particular element belongs to, so that you can have two such elements and check whether they are in the same set or not. So the two operations that we have are find, which says given the element x, which set does it belong to, and you're given two sets S1 and S2 and you want to combine these two sets. Okay. So before we dive into union find itself, let's see if we did not have union find, how would we approach this problem then? So maybe we could just use an array, so in which each element, the index is represents the element, and then on the value of the array we would see what set does it belong to. So AI is a group name or the set name. And when you merge two sets, G1 and G2 into one, then you iterate the entire array, and whenever you want to find, wherever you see G2, you call it G1. So essentially the problem with this one is that while the find can run very quickly in order 1 time, the merge will take order of n time, because you have to iterate the entire array and change the values. So in case of large number of finds and merge operations, it will essentially take a quadratic time. That's our main drawback while using an array here. So the union find data structure, the way it solves this problem is it maintains a kind of a tree data structure, but this is not a binary search tree, which we have covered in other lectures. And it's not even a binary tree. As an example, you can see here 3 nodes are pointing to the same parent node A. And the purpose of this here is that we say the A is essentially the element, but it also is then called the set name. So we reuse the element name to be the set name as well. So when we are calling the find on a set's member, we just return the leader. So essentially, if you call the find on the set B, on element B, it will traverse up and it'll say I'm in the set A. Same thing for element C, same thing for D. And also if you call the find on A, it will also say, because its parent node is null, so it recognizes that it itself is the root. So it says, okay, I'm in the set A as well. So all of these elements, A, B, C, and D, are in the set A. Again, I note that A is being used here as an element name as well as a set name, and that's perfectly fine. Okay, let's continue. Now, when we want to do a union here, the main difference compared to what we were doing with an array here, we simply point the root of one to the other. Which one do? We have a small preference here. Each leader maintains its height. Actually, in union find we use a slightly different concept called rank, but at the moment height can serve as a very good approximation of that. So when you're doing a union, you make the root of the tree with the smaller height to essentially point to the child, to be the child of the root of the tree with the larger height. So in this case, if A is here and M is here, you're doing a union. Rather than making M to be the child of A, you make A to be the child of M. And using this, we are essentially going to be able to maintain that the overall tree will not get too tall with respect to the number of elements that are in the tree. So we will easily get the order log n time for each find and union operation. So union will only take order 1 time, but the find will navigate from the root all the way to the root, the find will navigate from the node to all the way to the root, which will not be more than log n. So as long as we implement in this easy way, we will have union find will solve the major problem for us, giving us the login time, which we have seen is very efficient. So that's the main point about union find. We can kind of stop here, but there is another advantage or another trick used in union find, which is called path compression. And what the path compression does is that when doing a find, you navigate all the way from the node to the root. You might as well navigate one more time and now make the tree shorter by making each of the elements along the root, along this path, point directly to the root. So that's what the path compression does. There are quite a few different variations of path compression. Like you can actually even do path compression in one go, kind of like when you navigate from the parent to the grandparent, you already make it the pointer point to the grandparent, so kind of you would half the path. So there are quite a few variations, but almost all of them will give you this nice property that we're going to try to describe next, that they will make the overall time complexity to be even better. So path compression, even without path compression, we already had log n, but with path compression, the total time will actually decrease to log star n. Now what's log star n? Log star n per operation, roughly speaking. And the log star n is the iterated log, also called the super log. It's an extremely slow growing function and is defined as 0 if n is less than or equal to 1. Otherwise, you take 1 plus log star of log of n. And it has very interesting properties. So that's what is the trick of union find. And union find comes up very often as a good data structure, solves many different practical problems, all the way from insider trading, financial fraud analysis, terrorism, counterterrorism kind of operations. And how does it actually do it? Given 2 points on the board here, you can see whether these points are connected in the chip design kind of programs, click fraud, etc. There are quite a few different examples of this. The general abstractions that you can think about is that given a graph, are these two nodes connected to each other? Or another abstraction can be we're given this universe, and how can we organize these elements into sets? Exactly why it's called union find. As a small example here, you have these two vertices here. Are they connected to each other? U and V are connected to each other. We can of course try to do a find here. I'm not sure they're connected, but if we can use union find, we can easily find that overall this particular universe is divided into 63 components, and all of these are one component, and then there are some islands over here. So this can actually be done very quickly using union find. So that's a summary. Union find is a great data structure. It easily gives you the log n time complexity, but of course we can get even better by doing the path compression trick. The time complexity becomes log star n for many operations. Essentially for find operations, union is order 1 anyway. And log star n is so small that even though it seems like an expression of n, it's pretty much a constant for anything that we'll come across. You'll never come across log star n being greater than 6. So log star n, if for example is less than or equal to 5, actually 5 is a good bound too. If n is less than or equal to 2 power 2 power 2 power 2, which is equal to, if we calculate it, it's 2 power 6 5 5 3 6, which is a very large number. I mean, keep in mind that the number of atoms in the universe itself is estimated to power 250, and this is a much larger number than that. So there you have it, a quick introduction to union find. Just like binary search trees are magical, union find structure is magical as well. So hopefully this is good. Have fun, keep learning.